Hello, and welcome to the lecture for Chapter 15 from OpenStax Astronomy on the topic of the Sun. This is the first of two chapters where we're going to talk about the Sun. You can see this one is called, or subtitled, A Garden Variety Star. Well, the idea there is compared to all the stars throughout the galaxy and galaxies beyond our galaxy, ours is pretty typical. All right, it's not the most typical, but it's pretty darn close. It's right there in the medium size, medium lifespan type of sun, medium energy output, and all of that. So it's definitely a garden variety star. But it's still special for us because it's the only star that we have anywhere close. The otherwise closest star is a couple of light years away, which makes it essentially unimaginably far, considering a light year is 10 trillion kilometers. So that's great if we're considering stars and the survey of stars and something called the HR diagram, but that's a discussion for a class that focuses on stars and galaxies. In this class, of course, we're focusing on the solar system. So this is really concluding our discussion of the solar system by looking at the biggest thing in the solar system, our sun. Okay, so here is our local star, because the sun is a star, right? There are lots of different types of stars. This is ours. Okay, so the sun is quite an average star in many ways, as I said, but that doesn't keep it from being interesting. It does not stop it from being a fascinating object of study. I mean, it is 99% of the matter in the solar system. It dominates the energy of the solar system. It provides the energy that allows for life on Earth. There's a small amount of energy left over from cooling inside the planet and radioactivity inside the planet, but that energy is minuscule compared to the amount of energy we receive from the sun. The sun's magnetic field is super important for the solar system as a whole as it interacts with Jupiter's magnetic field, for example, because yes, the sun has a very strong magnetic field. The interactions with the magnetic field make for a fascinating and mysteriously hot upper atmosphere of the sun, which we'll talk about, called the corona. The sun, because it is so energetic and is creating so much energy, has a flow of electrons and other charged particles that spew out from the sun and wash over the planets, creating what's called a solar wind and solar weather, and that can directly affect life here on Earth or technology here on Earth. So it's relevant in that sense. So there's a lot going on, a lot of reasons that we definitely care about the sun, all right? But it's not going anywhere. It's very stable. It's in the middle of its lifespan. And although sometimes it releases a burst of energy, overall it's not in danger of blowing up or swelling in size for millions, in fact, billions of years from now, okay? A few billion years. So the sun is enormous, right? Here it is in comparison, right? Here's the size of the sun, and look, there's Earth, okay? It's over 1 million times the volume of Earth, over 1 million times, so 10 to the 6 times the mass of Earth, okay? So if you think of, the mass of Earth being on the order of 10 to the 24 kilograms, so about 1 trillion kilograms, the mass of the sun is on the order of 10 to the 30 kilograms, so over 1 million times the size or the mass, the volume of Earth, okay? In fact, it's more than 1 million times the volume because Earth is significantly denser than the sun, because the sun isn't made of primarily heavy elements. It doesn't have rock. It doesn't have metals. It doesn't have a metallic core like Earth does. Instead, it's made of much lighter elements, all right, which we'll talk about. It's quite an interesting aspect of the sun. Okay. By the way, this dramatic phenomenon here, this huge loop of gas, superheated gas, because that's what we're looking at here. It's not a flame, it's a loop of superheated gas interacting with magnetic fields. All ideas that I will talk about in some detail in the next few minutes. We'll look at its size compared to Earth, right? It dwarfs Earth. It's amazing, right? Because this is just one spew of energy from the sun, and something that just lasts a few days. All right, so I mean, this is a very transient phenomenon. These are just dramatic events that are constantly happening, right? So they have a spew of gas that's that large, and then have it dissipate within a few hours or days. It's amazing. So I mentioned that the sun is made of lighter elements. Well, the first person to discover that was this woman, Cecilia Payne-Gaposchkin, if I pronounce that anywhere close to correctly. And she was born in 1900, and she was actually the first woman to get a PhD in astronomy. So that was a breakthrough, but she still had a huge amount of hurdles, right? She wasn't just, handed that doctorate without some struggle. And she received it in 1925. The topic of the doctorate was actually about the composition of the sun, because she found through spectral analysis, looking at the light that came from the sun, that the sun was primarily hydrogen and helium. And this was completely unaccepted at the time. Even she was skeptical. Of course, it was probably an environment where her ideas, coming from a woman, were easily dismissed. So she was probably overly skeptical of her own ideas, but it is typical of scientists to be concerned when you get results that contradict the assumptions of the time, the scientific, reasonable assumptions of the time. Because at this time, in 1925, scientists thought that the sun must be made of heavier elements, that they thought it was a large, almost terrestrial-like planet. We also were not familiar with the composition of the gas giants like Jupiter and Saturn. And we had no idea that the sun was anything like them. We thought it was dense and hot and had a core of metal that was releasing all this energy. But that's not the case at all. The sun is composed of gas. Now, the gas is much denser than it would be in other circumstances because gravity has made it dense, but it's so hot that it can't phase change into something like a liquid. So it prevents the density from getting too dense. It is in a gaseous phase, okay? Unlike considering what happens inside of planets like Jupiter, where you have the upper atmosphere is all gas. They're called a gas giant after all, Jupiter and Saturn and Uranus and Neptune. But those gas giants, they don't have as much energy in their cores at all, nowhere close, and good reason for that. And therefore, the cores of the gas giants actually do phase change into a liquid and eventually a solid. So you look inside of Jupiter and you find a solid hydrogen core, hydrogen that has been compressed into a solid called metallic hydrogen. No such thing going on in the sun. The sun has a core that is releasing energy, preventing anything from condensing into a solid. The reason that the sun has a core that's releasing energy is because the amazing physical phenomenon of fusion. Okay, the sun has a fusion core. I have an arrow here that we can see on the red. So a fusion core. But that idea of the fusion that goes on inside of the sun is such a big idea and so important that it's a whole separate chapter. We'll talk about the actual energy production, the process of fusion in chapter 16. So kind of hold that idea. But for now, we just need to know there's a huge amount of energy being released. So that prevents this hydrogen and helium from ever turning into a liquid or a solid. So it stays as a gas, but it's such a hot gas that the gas is actually ionized. And when gases are ionized, they become a fourth state of matter, which is called a plasma. So you can think of the sun as being just a huge ball of plasma. Plasma is just a superheated ionized gas. Okay? That's what the sun is, right? A relatively dense ball of gas, but still just a ball of gas. All right? So what are the levels of the sun? Okay? Well, the levels of the sun involve the core, which we'll talk more about later. That's where the fusion happens, the really amazing physics. Outside of the core, things are more typical physics in terms of energy flow. There's a huge amount of conduction that happens in this zone right here called the radiation zone. Essentially, the energy is getting transmitted through this region. Photons have to pass through this relatively dense gas, transmitting the energy from one hydrogen atom to another, because although there's a lot of helium, there's still more hydrogen than helium, certainly a lot more. As you move out of this radiation zone, you eventually get to a part where the sun starts to behave more like the upper levels of a terrestrial planet like Earth, where we have our mantle, and the gas starts to almost have fluid-like properties. It's not as energetic, and that's where you get the convection zone. That's where the energy that was created inside the core is then getting driven to the surface of the sun through convection. All right. Here in the radiative zone, it was mostly really passing through something that kind of falls between radiation and convection because it's happening at such high density, or conduction, excuse me. But once we get to the convection zone, it's all about rising and sinking of the fluid being a gas, because a fluid, it can be both a liquid or a gas. In this case, it's in a gaseous phase. Right above the convection zone is the surface of the sun. And there's no, particularly solid surface of the sun, not even close. It's just, slightly different densities of gas. I mean, just like with the gas giants, there's nowhere you could actually land a ship, for example. And even if you were to, say, land on the surface of the sun, because the sun is so large, it has a huge amount of gravity. The gravitational acceleration at the point right above the convection zone, where you kind of get to the less dense, what you could call an atmosphere of the sun, is 25 times the gravitational acceleration on Earth. So you'd weigh 25 times as much if you were near the surface of the sun. That would crush you. It would crush a human, right? It's way too much gravity. You would simply be crushed under that weight. So that's big. In addition to the huge amounts of heat, that's another reason that would make the sun incredibly inhospitable and no way to actually travel humans to the surface of the sun. Now, above the surface, right, then we have the atmosphere. Now, the surface is best understood as what we see. Because you look up at the sun, you see a solid ball. That's because you're seeing the level that becomes opaque. Opaque in that no light can pass through it. It's not transparent to visible light, the visible wavelengths of light from blue to red. So everything underneath that is, there's still plenty of light there, but you can't see it. It's opaque to us as observers on Earth. That part is called the photosphere. Okay, so the photosphere is the part of the sun we see. Above the photosphere is the chromosphere. Now the chromosphere is not opaque, it is transparent. So transparent, which means that light can pass through it, the visible light, the lights of the rainbow, right? Even, less visible light, like infrared light and UV light, okay? Invisible light, really, not less visible, invisible to humans. But so the chromosphere is transparent. That's why we often classify it as the atmosphere of the sun, because it's above the part that we can see, okay? Above the chromosphere is something called the corona, which is the upper atmosphere of the sun, okay? So just like atmospheres of planets, terrestrial or Jovian, have these different layers that are defined by different characteristics, same with the sun. And in fact, the layers of the atmosphere of the sun are incredibly fascinating and are going to be a big focus of this lecture. So you can really think of this chapter, chapter 15, as primarily focusing on everything that happens above the surface of the sun. We'll talk a lot about the magnetic field of the sun, how the magnetic field of the sun interacts with its own atmosphere, how it creates lots of dramatic phenomenon, how it has a cycle, how it interacts with Earth. Okay, including Earth's magnetic field. But notice we will not be talking about the core of the sun because we're saving that for a future lecture. Now, where's the core of the sun? All right, so we're not going to be talking about the core of the sun or much of the interior at all, okay? All right, so hopefully that is clear. So moving on, one thing that we're going to be talking about in this lecture is the solar cycle, which is very much driven by the magnetic field. So if there's one kind of common theme, one big idea that you want to pay attention to in this chapter, it's that the sun has a magnetic field, and that magnetic field has a lot of effects, okay? So we can say much of the behavior of the sun is driven by its magnetic field. Okay, it's very chaotic, complicated magnetic field. It's magnetic field. Okay, I bring that up in this slide here because looking at this figure, we see sunspots. It's not the last time we're going to see sunspots. We'll talk about them more in detail, but it's one big thing about the sun. They've been observed for hundreds of years, since the 1600s, because with a basic telescope, you could see dark spots on the surface of the sun. They move with the sun as the sun rotates, as it actually turns about its own axis, because the sun is not stationary, it's rotational, as we should expect from conservation of angular momentum and the fact that the whole solar system was composed from a ball of gas that sped up as it collapsed under gravity. So the sun is part and parcel of that history of physics, and it's left rotating as well. It rotates pretty quickly considering how massive it is. It has a rotational period about its axis of about 24 Earth days. So it takes about 24 days, Earth days, for the sun to turn all the way around. We can track that rate of turning by falling sunspots, for example. Okay, we can find out how quickly they turn, and we'll see a slide of that. This one also shows the approximate size of the Earth, just to show how tiny the Earth is again. In this case, as instead of comparing to a big solar prominence, here compared to a dark sunspot. Why are sunspots dark, by the way? Well, I'll tell you in a minute. All right, so here we're looking in more zoomed in, more magnification at the surface of the sun. Notice the surface of the sun has this granulation pattern, okay? And this would be the part of the sun we see in the visible spectrum, so this is definitely the chromosphere, all right? Excuse me, the photosphere. The chromosphere would be right above this, okay? Yeah, directly above. So this is the photosphere, the part we see. And what we're seeing with all this granular pattern is we're seeing that bubbling gas, right? We're seeing that consequence of the convection zone. We're seeing all that energy welling up from inside the sun, creating these cells of bubbling gas. Because you can think of each of these as hot gas rising to the surface and sinking back down. And just like in Earth's atmosphere or Earth's mantle, gases that are being driven by convection create these convection cells, basically lots of circular structures that called cells that are next to each other. And they kind of look like animal cells, right? Or plant cells or something, hence the name. But the idea is that it's the top-down view of what on the side would look like a bunch of circles, okay? So if we were to look at the side view, we would see each of these as a circle of hot gas rising up to the surface, cooling as it releases its energy at the surface and sinking back down, okay? And there's lots of those. Now, they're not stable, right? Cells will merge with other ones. They'll fade over time. Then sometimes, and certainly a lot of times, since the sun often has sunspots, we'll talk about how often, there are these sunspots where you don't see solar cells. Now, why is that? Is this a hole in the surface? Have the cells collapsed? Are we looking down into a deep, dark hole? No, we're just seeing a part that is colder, okay? It is colder, thus darker, okay? So that's really just a consequence of how we're collecting light, how we're taking an image like this. So there is absolutely gas here in this dark region, this so-called sunspot, right? But it is colder, and that's why it looks dark. Why is it colder? Because it's interacting with the sun's magnetic field. What happens is there's certain sections of the photosphere that have basically got tied in with a strong magnetic field line of the sun. That strong magnetic field line is preventing the convection. Essentially, it's driving the motion of the plasma, this superheated gas. So the gas is then having to follow these field lines, these magnetic field lines, because the gas itself being ionized has absolutely a non-neutral charge, so it's going to interact with the magnetic field. So the magnetic field is essentially pulling the gas where the magnetic field wants to go. Well, that motion isn't allowing heat to rise up to the surface, so it keeps the sunspots cold. So the sunspots are much colder than the surrounding granulated convection pattern, okay? All right, so that's the idea. Sunspots are cold spots on the surface of the sun that are made cold by the magnetic field, okay? So this is a magnetic effect. And you'll hear me say that a lot over the next few minutes. Magnetism is so important in all these interactions, it makes so much sense. Electromagnetism is a big deal in physics in general, big deal in astronomy in general. And here we have a body, a star, our sun, that creates a very strong magnetic field and creates a lot of charged particles. What happens when you have a lot of charge and a lot of magnetism? You have a lot of interactions, okay? Because charged particles interact with magnetic fields. Charged particles create magnetic fields if they're in motion. So there's a lot of interactions going on here. Okay, so we can look at the sun's atmosphere in different spectra with different views. Okay, so in the naked eye, we see the sun as kind of a pale yellow color. It can change color, it can look more orange as that light passes through our atmosphere, and some of the light is scattered. The blue is obviously scattered, so we see an oranger sun. In space, it would appear more white. In certain atmospheres, it might appear more yellow. But regardless, that's the photosphere. We have one sunspot shown here, actually a couple sunspots. You can see a much smaller one. If we look in a different spectrum, if we look in, I believe, what's going to be, let's see, because if we're looking at the chromosphere image in the light of the strong red spectral line of H alpha, hydrogen. So this image is a falsely colored image that is just showing the spectrum of red for hydrogen. So just one particular spectrum for hydrogen, because all atoms, just kind of crash course here, we mentioned this a little bit before, but all atoms have a nucleus. Hydrogen has a nucleus with a single proton, and outside of that nucleus, you would have a single electron, all right? Now that electron gets ionized in much of the sun, but once you get to the chromosphere, it's possible for that electron to come back down to the proton, and then you can have energy transitions between the different orbits around the proton. So that electron can jump between energy levels. One particular jump corresponds to red, and that's just what we're looking at. We're just looking at this particular jump and the wavelength of red that's created due to that energy transition, okay? And that's a common energy transition in the chromosphere, so it's a good way to see the chromosphere. But if we look in a totally different part of the electromagnetic spectrum, and we look at X-rays, which are the type of energy or the type of electromagnetic radiation that's produced from inside of atoms, for example. So typically on Earth, X-rays are produced from nuclear phenomenon, so they're not terribly common. But it turns out that if you heat a gas up to about 10 million Kelvin, or about 1 million Kelvin, excuse me. So if you heat a gas up to about 1 million Kelvin, so 1 times 10 to the 6 Kelvin, then that gas, that now we're talking really hot, and I'll give you a variation of temperatures here, because 1 million Kelvin is exceptional. So that is the temperature of the corona. Let's lay that out as a fact, important fact. So the corona is about 1 million Kelvin. So the corona at that temperature emits black body radiation, according to Wien's law, at a wavelength that is in the X-ray spectrum, okay? Because every object has a direct relationship between the wavelength that's produced, or the frequency of light that's produced, and the temperature of the object. So as the temperature goes up, the frequency goes up, which means the wavelength goes down. You get shorter wavelength light. Well, X-rays are short wavelength light, so that means that they correspond to high frequency, which means they correspond to high temperature. Okay, so a hot gas that was, say, 100,000 Kelvin would produce UV light instead of X-ray light because it's still super hot, but it's not as hot to produce a wave that's so short to be an X-ray. Because UV rays, or UV light, is light that it has slightly longer wavelength, lower frequency than X-rays. Okay? And this, by the way, if you forgot the formula, this all corresponds to this fundamental relationship for all of the EM spectrum that says that C equals lambda F. Okay? So please review that if you need to. But the idea is the corona is so hot that it produces primarily light in the X-ray spectrum. Now, it also, due to interactions of those X-rays of other atoms and molecules, it also does emit light faintly in the visible spectrum that we can see during a solar eclipse. So when we block out the much brighter photosphere, when the moon, with its same angular size, passes in front of the sun, blocking out that photosphere and much of the chromosphere, we're left with just the corona because now we can see it. Normally it's washed out by the light, but it is definitely bright enough to see from Earth if it is the only source of light reaching Earth. So that beautiful pictures that you see during a solar eclipse, that's the corona. Okay, so I've hinted at the temperature a lot. Now the temperature, and this is all focusing on the temperature of the atmosphere of the sun, everything above the photosphere. Because as I said, we're not really looking in the interior much. We had one slide back here where we mentioned the interior kind of in passing. We'll get to it more. By the way, the core has a temperature of 10 million Kelvin. So let me write this correctly. So it'd be 10 times 10 to the 6 Kelvin. Okay, so that's the temperature of the core. That is by far the hottest part of the sun. But the second hottest part of the sun is way out here in the corona, which is really mind-boggling. Because you think about it, you might think that, oh, well, maybe the radiation zone or the convection zone is hotter than the corona. After all, they're literally inside of the planet or inside of the star. But that's not the case. And it's not even the lower atmosphere that has the higher temperature. It's the very upper atmosphere that has the highest temperature, and much higher. So look at the temperature of the photosphere. The temperature of the photosphere is about 6,000 Kelvin, okay? So about 6,000 Kelvin. There we go, 6,000, okay? And that's at a height of about 500 kilometers above the surface. That's right where, the sun becomes opaque, so that's the part we see, okay? Everything above that is transparent, as I said, so we don't see it except during a solar eclipse. All right, so it's still emitting light, just more faintly. Okay, but here's the thing, right? That's the photosphere. That 6,000 Kelvin corresponds to the peak wavelength of the sun, the fact that the sun appears white, which is the middle of the rainbow, but of course we've evolved to see the light that comes from the sun, so there's no coincidence there. It's right in the middle of the rainbow, so the peak wavelength of light, that corresponds to this temperature according to Wien's law, which I just mentioned before. That's this relationship here. It corresponds to green light because green light's in the middle of the rainbow. So in a sense, the sun is a green sun, but to the human eye, it appears white because green means it has just as much of the red, orange, and yellow as the blue, indigo, and violet. Okay, so that's the wavelength that's produced at this hot temperature, because 6,000 Kelvin is hot. That's well above the melting point of any metal, right? That's a really hot temperature. It's a temperature that can be achieved on Earth, certainly in certain industrial and scientific purposes, but it's really hot. But notice what happens. As we go up from the photosphere, we actually get hotter. The chromosphere is marginally hotter at a temperature of, let's see, it's going to be kind of still in the order of 1,000, because this right here, this is 10,000 right here, 10 to the 4. So we're probably in that range, okay? Kind of that range of halfway between 1,000 and 10,000. But then it does jump up until we get up to a point here where we have 30,000, as noted right there, okay? And then it continues to jump up really dramatically in the transition zone. Look, 10,000, 300,000, and then finally 1 million. So the corona has a temperature of 1 million Kelvin, okay? So that's way hotter. I mean, look at the difference, right? That is 3 orders of magnitude hotter. It's 1,000 times hotter in the corona than it is at the photosphere. How does that happen? How does the temperature jump up so much? Now, we've seen upper atmospheres have higher temperatures. In fact, that's a common phenomenon of the planets. But the explanation was always that the upper atmospheres were absorbing the high frequency, low wavelength radiation, the X-rays, the UV that's produced from the sun. And that's what makes those upper atmospheres so hot, because they're absorbing those really high energy photons. Well, that doesn't mean that they're hot to the touch or they hold a lot of heat. It just means they have a high temperature, because all upper atmospheres of planets and moons throughout the solar system are very low density. So yes, very high temperature, but very few molecules per cubic meter. So not a lot of actual heat contained up there. It's a near vacuum. But what's the explanation of the corona? Because the corona still has low density. So the idea here is high temperature doesn't mean a ton of heat, but there actually is a fair amount of heat because it's more dense in upper atmospheres of planets. But still, what's the explanation? Because it doesn't make sense that it's capturing X-rays, it's producing the X-rays. Now, are there X-rays that are produced within the interior of the sun, within the core? Of course, yes, there are higher energy particles coming out, but it's not enough to explain this jump. What creates this transition? What creates such a huge amount of energy, a huge amount of kinetic energy of particles in the corona? Why are they so energetic? Well, this is actually an incredibly complex question that's just recently big major breakthroughs in data analysis and better models have told us that it seems to come from just complicated interactions with the corona and the sun's magnetic field. So the magnetic field is what keeping the corona so hot. So we kind of just keep coming back to that magnetic field, right? But the magnetic field keeps the corona hot. All right? So it makes it hot, and it being the corona. All right, so that's the best explanation of why the corona is so hot. It's definitely an electromagnetic effect, and the magnetic field is interacting with charged particles, causing them to accelerate, bump around a whole bunch, get a ton of kinetic energy, and thus be very, very hot. Okay. Now, the corona, though, just isn't just out there, just staying hot and just being interacting with magnetic fields. It turns out that all the plasma that is existing in the photosphere and the chromosphere, well, sometimes it pushes its way up into the corona. So there's a lot of complicated interactions, which we're about to talk about. All right. In fact, here is a portion of that transition region where the temperature is so dramatically rising as we go from the chromosphere to the corona, where we actually see a relatively cool ribbon of gas, so cooler gas, that is getting kind of pushed up into the corona and traveling through it. Okay, so by cooler gas, it'd probably be on the order of about 10 to the 4 Kelvin, so only about 10,000 degrees, as opposed to 1,000,000 degrees. But it will gradually heat up as it stays in the corona. But sometimes it might sink back out of the corona. Okay, here is a picture of the corona. All right, we've blocked out a lot of the sun. We've blocked out the photosphere, the opaque part of the sun there. And this is similar to the starting photo from the slides, by the way. And we've also blocked out a lot of the chromosphere. So that's what's been blocked out here. So we're just looking at the upper corona. What do we see with the upper corona? Well, we see these effects where we have big strands of this very hot atmosphere that are sort of extending away, pointing in the direction of the solar wind, because the solar wind, which is, again, charged particles, right? So the solar wind is all these electrons, solar wind, which is mostly electrons, and some positively charged protons that are accelerating from the sun, away from the sun in all directions, while the corona kind of points along that direction of the wind. Okay, now the corona, this incredibly hot, I'd almost say mysteriously hot, but we understand it's an electromagnetic phenomenon, but very interestingly and fascinatingly hot upper atmosphere, sometimes, gets holes. It's very unstable, all right? There's a lot of dynamics going on here with the sun. And a coronal hole is a dark region in the corona where we can see through the corona down to the photosphere or even down to the chromosphere, okay? I said that backwards, but we can see down to the chromosphere or even all the way down to the photosphere, because, of course, the photosphere is below the chromosphere. I know I mixed that up a couple times, so don't get confused in that. Photosphere is what we see. That's the lowest. That's the opaque level of the sun. Above the photosphere is the chromosphere, okay? Above that is the corona. Now, what does it mean to have a corona hole? Well, in this case, since this is a image where we're looking at X-rays, it just means that we're looking at a region where X-rays aren't being produced because there's no hot corona there to produce them, okay? So it's just a gap. Now, the solar wind, okay, that solar wind that extends away for the hundreds of millions, 150 million kilometers out to Earth, interacts with Earth, okay? All those charged particles come bombarding on their way to Earth. Now, we have a magnetic field. That magnetic field absolutely protects Earth, okay? So our field lines make it so that the solar wind doesn't just wash over us. Instead, the solar wind that's coming in gets directed along our field lines. All right, so here's the solar wind, just passing over the whole solar system, and it gets redirected. The solar wind being charged particles, you can't have a charged particle, come in contact with a magnetic field and not get redirected. It experiences a perpendicular force that turns it. Well, then these charged particles get trapped and kind of take helical motions along the field lines, but eventually follow the field lines down to where they terminate into the actual surface of Earth. Where did the field lines terminate into the surface of Earth? At the poles. So that means that we have an interaction with these solar wind charged particles with Earth's atmosphere happening at the poles. What does that interaction create? Auroras. Okay, so the aurora borealis, for example, the northern lights, that is the interaction between the solar wind and Earth's magnetic field. Okay, the solar wind produced, passing through the corona, composed of charged particles. Okay, so now I've hinted at the solar cycle. Now we're going to spend a few slides particularly talking about it, okay? So let's start with the sunspots. So the sunspots are those regions where the magnetic field is so strong at the photosphere that it's preventing convection, thus creating cooler regions. So that's what we see here, cooler regions driven by strong magnetic effects right at the surface, okay? Those sunspots move as the sun moves. So here we can see it tracked over a few days in March of 2001. So starting in March 26th and then going up to May 2nd, we see that the sunspot has essentially moved from the side of the sun that we're facing all the way across to the other side. So essentially it's taken a track across, okay? And considering that we have, this is how many days? Let's see, so 4, all right, so 31 days, so we have 5 there, and then 7, so this is about 7 total days, which I guess I could have counted them because each one is a day. But the 7 total days represent not even a half. I guess this is about a quarter or a little bit under a third of the full rotation. But of course, we have to account for Earth's orbit because we're looking at different parts of the sun. So we have to account for the orbital period of Earth as well as the rotational period that we measure with the sunspots to correctly calculate the rotation of the sun. But it's been done many times and confirmed with different techniques. But regardless, we do see them moving because the sun is spinning on its own axis, okay? Now, an interesting thing about the sunspots is the way that they help us understand the sun. Because it's one thing to say, oh, the sun has a magnetic field and we see effects of the magnetic field, but a lot of times in science, we need a direct technique. We need a way of really confirming the magnetic field independently of what we see it doing, like creating coronal holes or creating sunspots or interacting with the solar wind, whatever it may be. We need to actually really confirm it, right? So how do we do that? Well, there's something that happens at the atomic level that is a direct consequence of magnetism in general, any magnetism. You could create it with a permanent magnet in a laboratory, and scientists often do. And that's called the Zeeman effect. Because it turns out that when hydrogen is in a magnetic field, and this is true of any atom, but here we care about hydrogen because hydrogen is the gas that's most common in the sun and in the universe. But the hydrogen in the sun, when it's in contact with a magnetic field, has split energy levels. So these are the energy level transitions that I mentioned in passing a few slides ago. The fact that any atom have electrons that can be excited between different energy levels. Those energy levels then correspond to the types of photon that atom can both absorb and emit. Well, when there's a magnetic field, there's a splitting of energy levels. So in other words, instead of the orbit, say, the second orbit having just one defined energy level, now it has 2 split energy levels. The magnetic field creates 2 possible, probabilistically possible, so the electron might or might not get excited to them, energy levels, okay? And that splitting is so directly measurable because we can get very precise measurements of it because we can take that light, we can put it into a prism or a complicated spectrogram, and we can see exactly where that split is. And that's shown in an image like this, okay? So it's an independent, very fundamental physics way of confirming that the sun has a magnetic field, and then of course used in aggregate, how we can then measure the magnetic field in different parts of the sun and its variation over time and so on, okay? So that's what it is, the Zeeman effect, fundamental physics that's used to understand the magnetic field of the sun. Now, the sun cycle, okay, the solar cycle. Here is our first slide calling attention to it. What the heck is it? Well, one thing that you want to kind of first understand is it's essentially an 11-year cycle, but 22 years total, okay? So it is a 22-year cycle, okay, with solar maximum every 11 years, okay? So most people refer to it as an 11-year cycle because for all intents and purposes it is. I'll talk about why the next 11 years is basically a repeat, but there is an important difference. That's why we call it a total of 22. So essentially there's 2 cycles to really repeat, but 1 cycle to repeat what we mostly care about. And what do we mostly care about, right? Well, look here, right? So here we have solar activity. This is shown in a non-visible spectrum. I think here we're looking at, I want to say UV, but I don't remember from this particular image, but we're looking at some part of the sun. By the way, this image is actually quite interesting. This is what's called a magnetogram. And a magnetogram is actually looking at the magnetic field. So this is not, there's no UV shown here, right? There's no electromagnetic radiation at all. This is actually just coloring this image or kind of pixelating it in either white, gray, or black, showing magnetic field strength. Okay, so it's just colored for field strength and polarity. So the black is one direction, well, we'll call it north, and then the white is south. So these are like poles of a magnet. So any place you see a black, that's a north pole of a magnet. Any place you see a white region, that's a south pole of a magnet. So you can see right away, unlike the Earth's magnetic field, where there's a north, on the geological or geographic south pole, and there's a south magnetic pole at the geographic north pole, and they're really right along the poles. In the case of the sun, we have lots of poles. It's a very messy magnetic field. There are poles throughout the sun. There is a dominant pole that we'll mention, but mostly there's lots of little magnetic poles shown here in this magnetogram. Okay, but what about solar activity and this idea of a solar max? Well, solar max is when there's the most sunspots. Now, it turns out when there's the most sunspots, there's also the most solar flares, there's also the most solar prominences, and also the most coronal mass ejections, all terms that I'll talk about in just a minute. Okay, but this would be solar max, the most activity. When you go then through solar max to solar minimum, where there's almost no sunspots and thus no other activity, and then you go back to solar max. Okay, that process takes 11 years. All right, so to go from solar max to solar min back to solar max is 11 years. But where does the 22 years come from? Well, when you do this the first time, you have a dominant magnetic pole of the sun where you have north-south like this. Okay, lots of little smaller poles throughout, but you have a dominant north and south. After you get to solar max the second time, the polarity switches. So then you switch from north to south like this, and you repeat the process. There's really no difference in activity or distribution of sunspots. It's just on a physics level, the poles have switched. So then to get exactly back to where you started with the solar max with the north where it's shown here, you have to wait two cycles of 11 years, hence the 22 years. Okay? All right. So here is the dominant poles of north and south of the sun. Sometimes they're pretty nicely aligned and there's not too much activity going on. All right, that would usually correspond to solar minimum. But then because the sun has different rotation rates, which we see with the gas giants as well, so there's definitely kind of a parallel there. But the sun has a equator that is rotating faster than its poles. And since it's not a solid, since it is, after all, just a plasma, it's a gaseous body, that's fine, right? The fluids can move in shear relative to each other. And so what happens then is, since the equator is moving faster than the poles, that fluid is pulling along, essentially affecting all the field lines that are passing through all these charged particles, creating sunspots, and that creates all these oddities in the field lines, including creating these weird little loops in the field lines. You see a couple of them here. Besides just creating, field lines that are all bent and twirled around, okay? All right, and these, so in other words, you have times where the magnetic field is nicely aligned with the actual north and south, geographic fields of the body, and then other times where the field lines are completely, all over the place and not really aligned with the axis of rotation at all, okay? So complicated, movable process that repeats every, 22 years, and importantly, has a max every 11 years. Okay, so that's the solar cycle, and just a simplified view of these messy magnetic field lines. Okay, so this is all the magnetic field lines. These things we've talked about a lot. This is really the first slide where we're showing field lines. Remember, magnetic field lines, they point towards south poles, they point away from north poles. They're electromagnetic phenomena. Okay, so here we are looking at other consequences of the cycle, right? So we got a few key terms essentially. Sunspots, we mentioned them quite a few times, cooler portions of the photosphere. But then above the sunspots are things called plages. Now, plages are essentially hot, dense clouds in the chromosphere, okay? They don't get talked about all that often, but here we're seeing some showing spectral lines of ionized calcium because it shows up very well. And yes, there are heavier elements in the sun. The only stars that don't have elements like calcium would be the very oldest stars that were formed right after the Big Bang, and because they never absorbed heavier elements. Our star, not being a first generation star, has heavier elements left over from previous stars that have died. Okay, kind of fascinating, right? It's picked up material left over from previous supernovas probably. And calcium is one of those heavier elements that was created inside of the core of a previous generation star. Now, it's been consumed by our star and exists, scattered throughout the mass of the sun. I mean, there's all the elements in the periodic table exist in the sun, just in smaller amounts. All right, so in this case, the calcium creates a nice spectral line, which is why we can see these white plages. Okay, notice that they tend to be clustered around sunspots. Okay, now on to something that's a little bit more dramatic, prominences, okay? Prominences are also driven by sunspots. They tend to form above sunspots because that kind of especially when you have a big cluster of sunspots during solar maximum, and that creates a disturbance in the electric field. And sometimes what can happen is you can have two magnetic field lines that will cross over each other. They'll cancel each other out and release a huge amount of energy because magnetic field lines carry energy. And if they're suddenly canceled due to effects of their chaotic nature within the sun, that huge release of energy is going to then push energy up away from the sun. All right, so an accelerate particles is going to create a particularly hot burst of gas, and that's a solar prominence. These solar prominences are cold compared to the corona. They have temperatures of about 60,000 Kelvin, but they're hot compared to the photosphere, because remember, the photosphere is only 6,000 Kelvin, so that 10 times hotter than the average temperature of the photosphere, which is why they quickly get buoyant and raise up above the photosphere, pushing into the corona, okay? Also, in the most dramatic example are solar flares. Solar flares are, a huge release of energy all at once, often, releasing energy in just a few hours, whereas solar prominences can last for days. There where you have, really clean cancellation of magnetic fields and thus a huge release of energy in a short amount of time. They're not fundamentally different than solar prominences, just more powerful. So instead of rising up slowly, they just create a burst, an explosion that's equivalent to, hundreds of thousands of nuclear bombs. That's equivalent to enough energy to power the United States for 100,000 years. Okay, the average energy consumption of our entire country for 100,000 years, and just created in a few hours in one solar flare, when there are, during solar maximum, a solar flare a couple times per day. Just to give you an idea of how much energy. Now, of course, the sun produces even more energy just radiating away, but these are bursts of energy that are unimaginably large. Okay. Now, these solar flares will then often cause a follow-up, which is called a coronal mass ejection, because that solar flare then pushes a huge amount of energy into the corona. That heats up the corona and breaks the corona apart, causes portions of it to accelerate, and actually will push a huge mass of corona, the actual gas, away from the sun. So you can think of a large chunk of the corona as achieving escape velocity. And that means it's going fast enough that it's no longer gravitationally held to the sun, and it's just going to accelerate away from the sun, going off into space, washing over planets like Mercury, Venus, and even Earth. Okay? Now, Mercury just gets bathed in these coronal mass ejections and just bombarded when it gets hit really hard. But it happens with Earth as well. So we often talk about the effects of solar flares, right? Solar flares can wipe out electrical grid systems, especially in the far northern and southern latitudes, like Canada or southern Argentina or Australia, places that are near the poles. Well, then you're going to have cases where if it's a particularly bad solar flare and a lot of energy released, when that energy reaches Earth a few minutes or hours later, then you're going to have a big effect. You're going to have all that energy come down through our magnetic field lines, come down to the poles. Yes, it's going to create some beautiful auroras, but it also can actually create resonance within our grid, and actually then can cause blackouts. Now, we've actually learned about that since the 80s, when it happened a few times, and as our electrical grid became more sophisticated, and we've actually found ways to design it to prevent against this. But we also have to stay aware. We have to always be looking at the sun, waiting for the next big solar flare, so we're ready, right? We can predict them, but we also want to be ready for them. Okay, here's the solar cycle, again, just showing from solar minimum to max, and then back to min. Okay, this is the 11-year cycle, so this is for a single polarity. Then we'd repeat it for a different polarity, and then that would finish the complete cycle. Okay, but you're still going to get a max every 11 years. Okay, here are the field lines created in active regions of the atmosphere. So this is during the solar max in different wavelengths. Okay, so this is showing the radiation that's produced. Okay, the radiation being when I say radiation, I'm not talking about nuclear radiation in terms of alpha particles and beta particles. Here I'm talking about radiation in terms of light. Okay, and I do want to point out that this would be for things like coronal mass ejections and solar flares. Well, let's get back to the actual numbers given here. So this is looking at 171 angstroms. What's an angstrom? Well, that's 10 to the negative 10. So 171 times 10 to the negative 10, and this would be meters, because it's a wavelength, okay? The way we talk about light usually. We can also talk about light in terms of its frequency, but more often we talk about light in terms of its wavelength. And I'll give us a grounding comparison in just a second. Well, if we move the decimal place over 2, that would be 10 to the negative 9, and then 10 to the negative 8. So we end up with 1.71 times 10 to the negative 8 meters. Now, to put that in comparison, visible light, like green light, the peak wavelength created by the photosphere of the sun, well, that's going to be around 500 nanometers. Well, 500 nanometers is equal to 500 times 10 to the negative 9 meters. And if we move the decimal place over 2, we're going to get 5 times 10 to the negative 7 meters. So we can see then that this 171 angstrom is a type of light that's about 10 times shorter, a little bit more than 10 times shorter than normal visible light, or at least the middle of the rainbow of visible light. So this would be invisible light. In fact, this would be X-rays, all right? Low energy X-rays, kind of right on the threshold of UV. As we get to 304 angstroms, this would still be a type of X-ray or UV. And then this one at 335 is definitely falling into the UV category. Okay, so the type of UV that causes sunburns, for example, right? All produced from lots of solar activity. And my takeaway here, what I want you to have as a takeaway, is that during these high periods of solar activity, that every 11-year cycle, when there's solar flares and solar and coronal mass ejections, well, what's going to happen is you're going to have lots of these high energy particles. Those are the ones you have to be concerned about if you're in outer space. Okay, because it's one thing to say, oh, they can come down through the field lines, hit the high latitudes and the low latitudes, cause blackouts. Yeah, that's important. But if you're, say, an astronaut living in the International Space Station, you are largely unprotected by Earth's magnetic field. Okay, there's still some field lines, but their direction isn't going to be as helpful. So that means that what's going to happen here is you're going to get hit by very strong, first of all, charged particles, and then second of all, light. Because this light, not being a charged particle, would not be affected by magnetic field lines and instead just hits Earth, okay? Now, Earth's atmosphere is going to absorb X-rays. Earth's atmosphere is very good for absorbing X-rays, so these X-rays will not make it to the surface, but they absolutely will bombard the space station. So that means the space station has to be protected against X-rays. It has to have shielding for X-rays, and the astronauts have to be ready for a particularly big burst of X-rays so they can get into parts of the station that are even more well shielded. They have to make sure they're not doing a spacewalk, for example, when that happens, because that could be deadly. It could cause cancer, because absolutely X-rays can cause cancer, right? Okay, and who monitors this phenomenon called space weather? NOAA. Same people who monitor terrestrial weather, okay? So here in the United States, space weather and the prediction and monitoring of it is done by the Space Weather Prediction Center, which is a subdivision of NOAA. So people are out here spending their careers, their expertise, making sure that we're safe on the surface, and especially astronauts are safe in space. Now, last thing we'll leave off on here is that the solar cycle is not just an 11-year cycle, because of course it isn't. The sun is 4.5 billion years old. It'd be pretty amazing if it just has one cycle that's 11 years, which happens to be shorter than a human lifetime, right? I mean, of course, it has to have cycles that are more on the scale of its incredibly old age. And one of those cycles we can actually see thanks to the incredible detailed work of tracking sunspots for hundreds of years. People have been tracking sunspots since the mid-1700s. I think it said 1600s a while ago. I think there is some data from back that far, but there's good data since the mid-1700s. And we can see that there's actually a variation that goes over those time, right? It's not perfect, but we can see there's actually a signal on top of the 11-year cycle, because every one of these maximums is 11 years apart, right? So that difference right there is 11 years. But then you can see that not all maximums are as powerful as others, right? There's actually a cycle, as I said, on top of a cycle, where maximums vary over a span of about 100 years, okay? And this has effects. It actually absolutely affects the climate, because during less active periods of the sun, there is less energy reaching Earth. And so there is probably some correlation between solar cycles and big climate changes like ice ages, okay? Well, there we go, talking about how the sun affects Earth, how the sun affects its upper atmosphere, and I guess how it's a typical sun, but mostly we've just been focusing on its magnetic field, its atmosphere, and how it interacts with Earth. In the next chapter, we'll get into its energy production, which is fusion. Thank you so much for watching this lecture. I hope it has been interesting and informative.